and good day. Today I'm going to talk a little about a very old concept, how it changed over the years, and the important implications and applications it has to today's world. While we're mostly going to be talking about buffer solutions, what they are, what they do, and why they are important, there are a few other concepts that we will investigate. Buffer solutions are aqueous solutions made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. Buffer solutions are used in a variety of situations, in pharmacology, fermentation processes, and even in the human body and in nature. Buffer solutions are used to maintain a relatively stable pH and the accepted parameters of the pH and amount of acid or base that can be added before the pH changes depends entirely on the acid and base used in the buffer solution. So, before we take a look at some buffer solutions and reactions, we need to dive into pH, pOH, and acids and bases so we can fully understand and appreciate these solutions. Søren Sørensen, a Danish chemist, is long since accredited with discovering the pH scale. He used it to describe the acidity of a solution while working for a beer company. pH and pOH are two measures of ion concentrations that allow us to characterize solutions as acidic and basic. Solutions with more hydronium ions than hydroxide ions we call acidic, and vice versa for basic. When the two concentrations of ions are equal, the solution is called neutral, like water. It can then be said that as pH increases while the pOH decreases, they are inversely related. The graphic at right shows the pH scale and some common solutions. pH is a measure of the hydronium ions in a solution or compound and can be mathematically described as a negative logarithm of the concentration of hydronium ions. pOH is the inverse. So it describes the concentration of hydroxide ions in a solution. Its formula switches out concentration of hydronium ions for hydroxide ions. These formulas are very useful and found in many other formulas. Now that we understand the chemical ions that define acids and bases, we can enter a very interesting time in the history of chemistry. The changing definitions of acids and bases. In 1883, a Swedish chemist named Arrhenius provided a definition for acids and bases. That acids are substances that contain hydrogen and release hydrogen ions in solution, while bases contain the hydroxide group and will release that into solution. This definition quickly ran into an issue. Some compounds, like ammonia, for example, that doesn't have a hydroxide group, in solution will still dissociate to produce hydroxide. So, in the 19th and 20th centuries, another Dane named Bronsted and his English colleague Lowry formulated a definition that was more inclusive. It focused on hydrogen ions. It says that in a solution, an acid is a substance that will lose or donate a hydrogen ion, and a base will accept or gain a hydrogen ion. As it happens in chemistry, another chemist comes along and revises the current theory or definition to reflect new discoveries and understanding. The current definition of acids and bases we use was proposed by an American chemist known also for his model of the atom, Lewis. His revision states that an acid is specifically an electron pair acceptor and a base is an electron pair donor, such that all Bronsted acids are Lewis acids, but not all Lewis acids are Bronsted acids. Now that we have reviewed acids and bases and the pH scale, we can talk about buffer solutions and the exciting mathematical formulas related to them. As we know, a buffer solution is a solution that resists changes in pH by neutralizing added acids or bases. Buffers work by replacing the protons and disrupting the chemical bonds. When an acid is added, the weak acid The weak base reacts with the protons to form the weak acid, and when a base is added, the acid loses a proton to the base, changing it into a weak base and allowing the changes in pH to be very minimal. The Henderson-Hasselbalch equation is another example of theory being modified over time to match new discoveries. The first part of this equation begins with Henderson in 1908, as he figured out an equation that can determine the concentration of hydrogen ions in a buffer solution. But in 1909, after Sorensen created the pH scale, it allowed Hasselbalch to redefine the equation using logarithmic functions and give us the formula we know today. The final equation shown in the slide is used when trying to determine the pH of a buffer solution. This equation requires the concentration of the weak acid and the conjugate base, as well as pH and pKa, which is a negative log of the acid dissociation constant, Ka. Okay, we have one final concept to understand before we can try a practice problem with the Henderson-Hasselbalch equation. It should be noted at this point there are some limitations of this formula, especially when the buffer solution is very diluted with water. It does not take into account any dissociation that occurs within water, and also struggles when the buffer solution uses strong acids and strong bases. Exactly why, previously, we defined a buffer solution as a weak acid and a weak base. The acid dissociation constant, Ka, is the equilibrium constant for reactions of weak acids in aqueous solutions. Weak acids have a smaller Ka value, shown mathematically in its formula, where Ka is the concentrations of the hydronium ions times that of the conjugate base over that of the weak acid. Water is not included in this equilibrium calculation as it is a pure liquid, and thus we know its activity to be 1. So now that we have defined all terms in the equation, let's see if we can't use it to solve for an unknown pH. For this practice problem, we have a mixture of acetic acid and sodium acetate created at molar concentrations of 0.15 molar and 0.22 molar respectively. What is the pH of the mixture if acetic acid has a Ka value of 1.7 times 10 to the negative 5? To begin, we write down our givens in the left column. The concentration of acetic acid, the concentration of sodium acetate, our Ka value. We know that we must use pKa in our Henderson-Hasselbalch equation, so we convert Ka into pKa by taking the negative log of Ka. The negative log of 1.7 times 10 to the negative 5 is 4.76. We also write down the Henderson-Hasselbalch equation that we will be using. pH is equal to the pKa, which we just derived, plus the log of the concentration of the conjugate base divided by the concentration of the conjugate acid. We know that acetic acid is the acid, the weak acid, and sodium acetate is the conjugate base. We can now plug our values into the formula. We take the log of the different and add it to our pKa value. We get a pH value of 4.92. I hope this practice problem made sense. Thank you for listening, and I hope you enjoyed this blend of history and the chemistry that it created.